name is Ana Mijic. I am leading the RIWS project, which is funded by DAFNI, and RIWS stands for Resilient Scenarios for Integrated Water Systems. I'm going to present the work, but the real work and the great results that I think you will like has been done by Dr. Liang Liu. You want to so any tough questions, of course, will be for him. So just a bit of a background, the work we do at Imperial is around integrated management of water systems, and this is just a very high-level representation of what we mean by integrated water management. We heard a lot of notion around the integration today. What we want to integrate in the modeling is the element of the natural environment, of the resources side of the water system, wastewater side of the system, and the component around the people and the use. So the DAFNI project is about using and adding a model that we have been developing since 2019 now. It's called WSI mod. I'll tell a bit more about the model, but the idea around the DAFNI project is to add the tool to DAFNI platform, and then, as the title of the project says, use that to develop resilience metric for integrated water system, and then use that metric to develop a way of doing adaptive planning for the integrated water systems. So we have started in October last year. The progress has been good, so we have split the results in 3 parts. So one is the pure technical development, which means adding the model to DAFNI. So if you go to DAFNI platform, you will find the version of the model, which is what we call our default version. With another example, we will be adding our case study example by the end of the project. And what we are doing at the moment is developing functionality for WSI mod to be able to do customization. Customization means that you can then change any default structure, a node or link in the model, and you can also run sensitivity analysis. So we're also collaborating with one of the other projects that's led by Dr. Francesca Pianossi at the University of Bristol. On the research part, we have split the work in 2 bits. One is the resilience metric development, which I'll talk about today mainly, and then the work that Leon is doing at the moment, which is around the adaptive planning, and I'll just show some preliminary results. And then the third part of the project is around the engagement. We have really lovely project partners. We had one workshop where we presented the resilience results, and I'll just show some of the insights from that one, and the other one will be held at the end of the project. So what is WSI mod? It stands for Water Systems Integration Modeling Framework, and if you scan the QR code, it will take you to the paper that has been reviewing the code. So the code has been reviewed, as well as the theory and applications behind that. The components that you see are different elements, and this is what we call the generic setup. And those of you who are in the room will recognize the components of the integrated water cycle. So what the tool does is representing each of these boxes as a node. So there is a small model behind each of these boxes. And these arrows are the links which could be also defined. So any element in any part of the system can talk to another element. And kind of coming back to integrated view, we simulate water resources in a relatively simplified way compared to, for example, some of you have seen the presentation around the PyWare. But we do represent water resources. We represent the land use, urban, rural, around the water use, but also fertilizer applications. We model the wastewater processes, and then ultimately all the results are integrated at the catchment outlet. So default simulation spatial scale is the water catchment, but the model can see different resolutions as well. So most part of the work done so far has been done on the resilience evaluation for integrated water systems. What Leon did there is to start with a very basic definition of resilience. So it's dynamic resilience, which is measured by the performance of a system, which is then stressed and goes into the disruption event. So what Leon did is to redefine that to propose not only one upper, what is vulnerable threshold, but also another critical threshold where the system becomes highly vulnerable. And then he defined the ways of aligning the definitions for the different elements of the water system at the event level. So what we see here is the event level, but also annual level and the system level. What that enables us is that we can now have the measure, which goes from 0 to 1, for different components of resilience, but also different elements of the water system. And for this work, we have chosen 8 components to look at separately. So on the supply side, we look at the obstruction-demand balance for the urban water use. We look at the groundwater availability, which is important in our case study. On the wastewater side, we look at the quality aspect. In this case, the combined sewer overflow ammonia concentration, and on the flow side, the sewer flooding risk. And on the environmental side, we look at 2 indicators for flow, high and low flows, which define the risks of floods and droughts, and then 2 water quality indicators that define the status of the environment from the WFD perspective, Water Framework Directive perspective. And then if you set up the model, if you run the model, this is what you would get by default. This is our case study. It's a Luton catchment in north of London. The model is set currently for the 8-year simulation period. The simulations are daily, and the red are the simulations, and the blue are the observations. So we validate the model with the publicly available data, and I should say that all the data that come into WSI mod, apart from water resources, are publicly available data. For the water resources, we need to get into the agreement with water company. In this case, Affinity Water has provided water resources data, which are included in this. And you can see performance measures, which are relatively good for simulation models, for the flow, which is top diagram, and then nitrogen and phosphorus for the bottom 2. So if we have now time series, we can then process these time series to look at different resilience indicators. And I'm going to just show a selection. We can have a chat with Leon about all the other elements. At the event level, we can look at 4 characteristics. So it's those who work in the resilience that would know about the 4R metric. I'm going to show just 2 of those, which is response and robustness. And you will see the results split in these 4 squares. And at the very high level, so the top right is good. And then if we do that for all the elements that I mentioned that we're going to analyze, we see quite high level of variability. So first we see that some systems go into the critical and vulnerable state much more often than others. And we also see that these events, so each dot is one event, there is not much pattern in the way what happens with different subsystems. So we're just going to zoom in into a couple of interesting findings. So this is these are the 2 subsystems or 2 indicators where the system generally performs relatively well. So drought means low flows in the river and the phosphate concentration in the river, where you can see here that most of the dots, so these are the percentages of the points, most of the events are in this top right corner. It means that the system doesn't go too much into the vulnerable state and recovers really, really quickly. But then, of course, this is not the whole story, and especially around the water quality, and we'll see that kind of pattern. That pattern that does show up. If we see now this top right box, we see that especially on the phosphate and especially nitrate, we see very high percentages in this area where the system it recovers relatively quickly, but it has very high dips or very high impact events, which is of course very challenging from the pollution management perspective. And then the last one, which we're going to take forward for the adaptation example, is the flood. So these are the high flows in the river. It's not flood on its own, it's the risk of flood. You can think about it in that way, where we see the variable performance. So we see some of the events which are, say, relatively good. They do happen really quickly, and it takes them a bit of time to recover, but they're not very significant. But we also see a significant percentage in this top left-hand corner, which is the most vulnerable one. So we really don't want anything to happen here, and we see for the flood, we have these events which are very destructive and last for too long. And then if we have this information at the event level, then we can start, and this is why it's called bottom-up framework, we can start aggregating things. So this is the example of the aggregation per component. So you see different components here, and then all 4 elements of the event-based metric. And these are results, for example, for the 2019. So we can look also at the annual level. And we see the pattern that slowly emerges from the data. And this is that if we compare the infrastructure side of the resilience and the environmental side of the resilience, it's the environmental part that suffers. So we see here that the system is much less resilient from the perspective of water quality, and in this case also the groundwater resources. And then if we aggregate everything at the system level, so this is when we can compare directly different components of the water system from the resilience assessment, we see what we like to call winners and losers. And so the systems that are designed with the resilience in mind, which are the supply and wastewater systems, generally perform relatively well. Of course, this is the 8-year snapshot. So if we increase, we may see different performance, but generally you see the resilience, quite high. While if we look at the water quality indicators, which is nitrate and phosphate, and I should say the threshold set for nitrate and phosphate are the regulation thresholds. So some of the threshold has to be set by infrastructure operators, some of the threshold is set by the regulation, and from the environmental regulation, nitrate and phosphate definitely in Luton have a huge problem and very low resilience. So with that in mind, what we can do now, so these are all historical simulations on evaluating resilience historically. What we are working at the moment, what Leon is working at the moment, is saying, okay, if we have all of this information, can we use resilience as a metric for adaptive planning? And what we did there is to choose as a proof of concept the flood resilience as our target resilience, and what we are developing and testing now, so these are very preliminary results, is what it's called the multi-stage approach. Multi-stage approach means that if we're currently working with 10 years period, so if this is the historical period and this is the point where we need to make a decision, we can do climate scenarios, we can choose and calculate the performance of our system as now. We can define different portfolios of different interventions, and depending on our preferences, which is where the decision element comes in, we can choose and implement one portfolio. And again, there is lots of detail around how we can choose, and we are playing with different types of preferences. But what that gives us, and if we do that every 10 years, what that gives us is a diagram like this, and those who have done adaptive planning will recognize these diagrams. So this is the level of implementation across, I think, 40, 50 years. And you can see there are these jumps every 10 years, which is when we make a new decision. We are working with 4 options. And what is interesting here, we took the historical period just to do the comparison, because we can have this, what we call the most ideal. So what would be the decision if the future would be completely certain? And you can see here that there are some differences. So we are definitely maybe over-implementing, say, regenerative farming and so on at the very beginning. But if you look at the resilience assessment, you will see that this blue line, which is our decision on the deep uncertainty, is actually performing very similarly to something which you would choose if you would know the future perfectly. And you will also see this straight line, which is our setup value of the threshold. So the decision process is set that the options need to be implemented if the resilience goes below 0.7. And then the last one is, of course, we also track the cost and our uncertain decision-making and deep uncertainty is the blue one. So our cost, of course, is higher than the ideal because we don't know what the future is going to be. But you will see that the investment periods are relatively similar, and considering that the system achieves the desired resilience, even with a high level of uncertainty, this is possibly something that could be taken into consideration by the decision makers. But again, we are playing a lot with different, there's lots of subjectivity in the criteria that we have to impose here, and we are doing lots of sensitivity analysis at the moment. So what we're going to do next, so we have a couple of more months of the project. We have done a first set of engagements. So this is, I mentioned that there was a workshop. We had representatives from Affinity, Thames Water Environment Agency, GLA, and Mott MacDonald. So these are all our partners and collaborators we work a lot with. And what was interesting and what came very strongly from that workshop is that they liked the way of doing the resilience for the integrated water system, and they do agree that water quality is a very interesting and very important indicator. They gave us a lot of recommendations of what to do next, and these are these recommendations in the boxes. Zooming in on water resources, thinking about the assessment locations. At the moment we're using only the catchment outlet, using the planned options or options that are in current plans and putting them through adaptive planning and so on. So we are currently looking into the feedback. And then finally, I guess the brief was, what do we think is going to happen next with this? What I would say is that I think there is a huge need for evaluation like this, especially the policy level and the regional planning level. We do want to keep these resilience, which is high. We want to keep it high, but we want to definitely improve the resilience of the environmental systems with climate change, with the development that will be very tricky, and with all the results, we do see that trade-off between the development and environmental protection. Is it possible? I mean, I don't know. I think it is. I think if we look at everything in a coordinated way, it could be, at least we'll have the information to make decisions and communicate those decisions. The role of government was mentioned this morning and today. This is the very nice document that I would warmly recommend if you want to have a look. This is the document that was just published by the Institution of Environmental Sciences, which is their recommendation on the actions for the new government. And they specifically say that the supporting the delivery of a systems approach to water with models of an integrated water systems is something they would recommend. We could not agree more. So we hope that this is one way forward, and DAFNI is definitely something that maybe a use of that could be enabled. So that is all from me. Thank you.